Welcome everyone to Cloud Frontiers, a deep dive into serverless spatial data and FME. So this is the follow-up part 2 webinar on our cloud native series. Today I'm joined by Dean and Kaylin. Dean, would you like to introduce yourself?
Yeah, sure. So my name is Dean Hintz. I've been with SAFE quite a while, kind of lost count, and I head up the strategic solutions team, where we do sort of kind of advanced prototypes, with new application areas and new technologies. And so cloud native is, I guess the other hat I wear is open standards, and cloud native certainly does fall under that category because all the standards we're talking about today are open. So yeah, that's me.
Awesome. And Kaylin?
Hey, yeah, I'm a technical support specialist for the FME forum side, so you can typically find me kind of poking around on the forums or helping out with cases.
Fantastic. All right, and also note we have Natalie joining us on the back end to support with Q&A. So if you do have any questions that come up during the webinar, please drop those in the questions tab on the bottom right there, and we'll have a little bit of time remaining at the end for Q&A. Perfect. So welcome to Livestorm. If this is your first time in the platform or if you're newer, click the help button on the bottom left if you have any issues with audio or video. Share your emoji reactions with us during the webinar with the react button on the bottom middle. We'll have a poll coming up in the bottom right tab as well under polls. And as I just mentioned, any questions, please do drop those in the questions tab. And yeah, keep letting us know where you're tuning in from in the chat there. All right, so at this point, I'll get our presenters to turn off their webcams just so we can save on some bandwidth for the rest of the webinar. And I'll also pass it over to Dean to get us started with our agenda here.
Yeah, so I'm excited, as I said, to dive into cloud native. I think this really fills a niche that has been missing for a while in terms of how do we optimize geospatial data over the web. There was a really good initial webinar on this with Chris and Michelle, and I certainly recommend that anybody who missed that, check it out. But yeah, we'll go over briefly, just a quick recap from that about what is cloud native, what are we talking about, and then we will dive into, this is more of a deep dive, so we're going to focus more on demos. So we'll look at STAC and COG, FlatGeoBuf, COPC, which is the point cloud, and ZARR, which is more of a data cube, and then GeoParquet, and then we'll hopefully have some time for questions. So just before we get going, I guess we have a poll here.
Yeah, so I've just published that under the polls tab there. So if folks want to head over, we'll give everyone a moment to vote. But yeah, we'd love to know what's your leading motive for considering the use of cloud native. And we don't have an other option, but if there's another one out there, then feel free to drop that in the chat too.
Yeah. If there's any feedback you want to give that isn't, like, for example, an option that isn't on the poll, then we will be tracking the questions in the chat and hopefully can address some of those in the Q&A.
Yeah. All right. It already looks like we have most votes in here. And we're actually pretty split between the top 3 or 4. Data distribution, performance improvements, faster, lighter web applications, cloud-based workflows. Is that kind of what you'd expect, Dean and Kaylin?
Yeah, I think that aligns pretty well.
Yeah, that is surprisingly even though. Yeah. And we are focused primarily on consuming data from these formats. We'll talk a bit about writing as well. But yeah, if you're looking at, for example, writing to something like STAC, we welcome your feedback for that as well. Okay, so moving on. So let me just dive in here and talk a little bit about what do we mean by cloud native. Essentially what we're talking about is optimizing our data stores so that just to make it easier to access and more efficient. And so it's those two terms are kind of used interchangeably, cloud native or cloud optimized. And what that actually means is sometimes we have to do a little extra work on the front end. So the loading of the data or the generation of the data can actually take a little bit longer. But what we're doing is chunking or indexing, tiling, and generating metadata so that ultimately the response is faster. So what we want to avoid is, having gigabytes of data where you have to go to an FTP site, download everything, and then extract, what you need for your city block that you're working on. So that's kind of the whole idea. And the bottom line is, you'll hear this, say this about, we'll repeat this mantra throughout the talk today. The goal is to read just what you need. And so you don't want to read everything. And ultimately, this allows us to support thin clients on the web, whether that's in your browser or a mobile device. So there's a few other terms that we hear when we're talking about this. One of them is lazy evaluation or lazy access. And it doesn't mean that we don't want to do real work. Lazy just means typically what happens in lazy evaluation. You define the whole data flow, but then the writer makes a request back to the reader about what it actually needs. And so if there's let's say you have A and B and C, and you have an intersection across all those, a lazy evaluation would essentially be an AND function across all those, where you only request the extents of the data that you need for, the intersection of all of those. So this helps better support data integration, analysis across distributed systems, and ultimately more scalable performance. And also on the data provider side, it reduces the cost burden, because whoever's providing that, somebody has to pay for the data download for these cloud data stores. And we've noticed 50%, 60% plus cost savings on data download burden when people are making use of cloud native. And basically the goal is to leverage scalability, flexibility, and processing power of the cloud infrastructure for large data volumes. So just a quick example of this. I'm just going to go in here and open up COG. Notice that it says COPC here. I have to be a bit careful, because if I forgot to change the reader, we could be stuck for half an hour. So that's one word of caution on this. So this is a 32 gigabyte data set that covers all of Canada. It's a digital elevation model. And actually, sure, blank this out. I don't want to read Pyramid 0, or Pyramid 1, I should say. So you can see it goes away and it comes back almost instantaneously. And so that's pyramid level, whatever the top level is. And, pyramid level 10. And then if I want to do pyramid level 1, which is 30 meter, now obviously I'm not going to request all of Canada. In this case, I'm just going to have a preset. And now I want the 30 meter data just for Southwest, or the Vancouver area. And goes away and grabs that. Takes a couple seconds longer because it is getting the full resolution. I also wanted to quickly demo what happens is if you forget to do this. If you don't set the coordinate system, it will complain. Okay, it'll say basically that's required. So, CanLam 83. So, yeah. And you can see that this is pretty detailed data now. I can zoom in here, North Vancouver. I can look and see that, in fact, that this data is 30 meter spacing. So that's from a 31 gigabyte data set. So I thought that was kind of cool. So basically pyramid level 1 is the lowest zoom level. And I guess, I'm not sure what the theoretical maximum is. It's up to you when you generate the data. So of course we support both reading and writing. You can write this out And this is based on the GeoTIFF standard, so it's kind of COG is a layer on top of GeoTIFF. So any GeoTIFF reader can probably read a COG, but it has to be sort of COG aware if it's going to actually drill into those different pyramid levels or request the extents. So you do need a COG aware reader and writer to benefit from the cloud native side of it. And yeah, so it's a 16-kilometer grid cell when you're at the lowest zoom level and a 30-kilometer cell when you're at the highest. And so, yeah, you can see how this is a pretty handy resource that anybody in Canada could use to grab a DEM. So that was just a little flash demo to get your feet wet. I just wanted to give a nod to both Michelle and Chris. They are definitely what I would call industry pioneers. And they've, Michelle's been involved. She's from Radiant Earth and been involved with cloud native geospatial for quite some time. And Chris Holmes, he's kind of a household name. And he's been involved with STAC and COG pretty much from the get-go. And so in the last webinar, Michelle did a great job of doing some comparisons across the various cloud native formats. And Chris kind of traced out the history of the development of cloud native. And he also made some really good points about what are we talking about when we talk about spatial data infrastructure. Because we can build things that, architect things, but SDI really shouldn't be for the author. It's really about the consumer. So check out the last webinar if you missed that. So just a nod to Chris Holmes and Planet. Obviously they work with this stuff every day, and Radiant Earth and Cloud Native Geospatial. So there's that comparison table, which looks at things like GeoTIFF, NetCDF, and then the equivalent cloud formats and some of the trade-offs there. And you can dig into that, or that'll be available in the deck. So just in terms of a bit of an update about where we're at in FME support, we introduced support for COG, Cloud Optimized GeoTIFF, the one you just saw for the Canadian DEM. We introduced that back in 23.0. And then we added, FlatGeoBuf then, and then GeoParquet and Cloud Optimized Point Cloud came in 23.1. But I would really strongly recommend, these are all quite new. And so I would strongly recommend the latest release, which is 2024.0. I think it's .0.1 and .2 is going to probably be out in a couple of days. So I would recommend FME 2024 for sure. And that will also allow you to, Kaylin's going to talk a bit more about the package necessary to read STAC. So speaking of Kaylin, why don't I hand it over to you, and we can dive into the wonders of spatial temporal asset catalogs.
Thank you. I'm just going to take a second to share my screen. So the way we have this set up is we'll kind of briefly review the format. We'll take a look at the format in FME, and then we'll run you through a demo. So can everyone see STAC? Yeah?
Yeah, looks good.
Awesome. So in long, STAC stands for Spatiotemporal Asset Catalog. STAC is a nested cloud-based format that's structured in JSON. So a STAC catalog can have one or many collections. A collection may have one or many items, and an item may be comprised of one or many assets. Within STAC, we can refer to assets as the actual data itself. Assets can be vector or raster, so we can actually store a GeoPackage layer as an asset or a single COG band. So the STAC format is available on FME Hub as a package. You'll need a minimum 24.0 build to access version 2 of the package, which will contain the STAC metadata and asset reader. The main difference between said readers, besides the type of content being read, is the item level selection. So the metadata reader will automatically read all item assets. So you'll receive metadata for each asset within the selected item, whereas the asset reader will actually allow you to read specific assets from an item. So maybe if you're working with hyperspectral data and you have hundreds of bands, you can then go ahead and actually just access a few. So this slide is supposed to show you how you would kind of use the reader to dig down into a STAC collection. So within the STAC parameters, you can see that we have some options to control filtering. So here we have temporal and spatial filters. So for temporal filters, you can specify a to from date range, so like 1999 to 2000, or you can select the latest. And latest will refer to the latest date. So it will show items that were published to that collection today. Switching over to the spatial filter, this kind of works similarly to a search envelope, but it's not quite the same. So the reader will use these extents to cycle through and present items that fall within that spatial range, opposed to clipping or reducing the data. So this brings us to our first demo. So here we're going to read a stack, do some post-processing with raster transformers, and then publish to Amazon's S3 as a COG dataset. I think we're just going to play a video now.
So in this demo, we're going to use the STAC asset reader to consume a STAC item, remove no data, convert to cloud-optimized GeoTIFF, and then upload to Amazon's S3. The item being read is a mosaic GeoTIFF of Houston, Texas after Hurricane Harvey in 2017. So to get started with our translation, we're going to use the STAC asset reader. You'll notice dataset is grayed out, and this is because STAC typically exists in a cloud environment. So here we're going to change the STAC URL type to catalog, and I'm going to paste in my catalog URL. From here, I'll use the reader parameters to select my collection. In this case, we're going to be selecting planet disaster data, and I'm going to continue to select items until there's nothing left in my menu. Next, I would apply spatiotemporal filtering if needed, or I can use the item parameter to select my items. So here we're going to be working with Houston East RGB mosaic image, and we'll select our assets next. So we're just going to be working with the mosaic, and we'll hit OK. Now we'll see our reader feature type added to the canvas. Before building out the rest of the translation, let's take a look at our data. Awesome, so the image is coming in properly, it's geo-referenced, but there is this black kind of no data border, so we can use an FME transformer to remove that before converting the file. One thing I will do is go in the format attributes on the reader feature type and actually expose FME base name, so I can use this in parameters downstream. To remove the no data, I'm going to type on the canvas using the quick add function to select the raster band no data setter. In this case, our no data value is 0. And then we can add a feature rater to translate the stock to a COG. Our format will be cloud optimized GeoTIFF, and our dataset can go to the output folder. We're going to want to change the raster file name to FME base name, and then we're going to want to set the file structure. In this case, because it's high resolution imagery, I'm going to set it to 5112, and I would also maybe apply compression. Next, we're going to use an S3 connector to upload that local file to Amazon S3. We'll do this by selecting a web connection, inputting our region, hitting the upload action, and then pointing it to the file. In this case, I'm going to use attribute values to actually create the file. To create the file so that it's more dynamic. Sorry about that. Paste issue. We'll select the bucket the file should be uploaded to, and then the path. So we're going to store this in our cloud native webinar and then COG folder. We're going to click OK, and then we can run the entire translation. Expand the log file.
And we've successfully written our COG to Amazon S3. Okay, so that was our demo. So there you saw us read a STAC asset. We removed no data, and then we wrote to S3. So just a quick summary, you can use raster transformers to post-process stack assets, whether it's removing node data, mosaicing, or combining raster bands. And then FME's S3 connector can push data sets like COGs to the cloud. So here is our output again. Screenshots are taken in the FME data inspector, and we can see that it's resampling kind of quite quickly, actually. So just kind of an overview of STAC and FME. So you'll notice that a single feature type will only access or read a single item collection. So if you're looking to read multiple items or items from different collections, you will require multiple readers. And then just to touch on what's coming, or should I say coming very soon, authentication support is slowly being added for major service providers like Microsoft Planetary Computers, Sentinel Hub, weather layers, and I think I'm missing one or two more, but really this just means that these authenticated stacks will be easier to work with and interact with in FME. So this brings us to our next format, so COG, or in-long cloud optimized GeoTIFF. So COG is a raster-based format that's built off the GeoTIFF specification like Dean mentioned earlier. So it similarly supports pyramiding and compression. The benefits of COG can really be seen through partial reads, and that goes back to that whole concept of read what you need. So this can be done through min-max extents and or clipping. So taking kind of a closer look at the format in FME, we can see the search envelope options and pyramid level options on the reader here. So you can kind of refine and reduce what you're bringing in and working with. And then I'm just going to switch gears to the writer. So on the writer feature type, under the file structure parameters, we have this layout option. And there you can select cloud optimized GeoTIFF and then either match a tiling scheme or enter custom tiling values. So these parameters down here will specify the size of tiles to create on the output. So this is a COG with a search envelope applied. So screenshots again are taken in FME data inspector. And to kind of see what this is doing, I'll skip to the next slide. So really we're reducing the amount of desert kind of imagery that we need to process at each step of the translation. So maybe here we're really trying to enumerate the amount of healthy fields in the image or apply some kind of analysis index like NDVI. If that's the case, we really don't need to be processing all this additional data. So this brings us to our next demo. So here we're going to create an interactive fire report showing fire points overlaid on a DEM.
Perfect, and we'll share that demo up here now.
In this workspace, we're going to be using FME Form to author a workflow that creates an interactive HTML report of recent fire incidents in British Columbia, just west of the Kelowna area. Both source datasets are being read from S3. We'll be reading a FlatGeoBuf of fire points and a cloud-optimized GeoTIFF DEM. We're going to start by authoring an FME form and then processing down the road in Flow. So firstly, let's read in our data. So I've gone ahead and cached these readers. You'll notice that I've applied a search envelope on the FlatGeoBuf reader, and so we're only reading data that overlays with our raster extents. If we take a look at the data, we'll notice that there's still some points that are within the raster extents, but they're actually in the no data areas of the raster. And so we really should refine or remove these before writing to HTML. To do this, we can create a polygon mask to clip with, and this will actually filter out these points. So to get started, we can go ahead and send our raster to a raster cell value replacer. And here we're reclassifying everything with data to be 1 and everything with no data or invalid data to be 0. And this will create a binary grid for us. Once we're happy with our binary grid, we can go ahead and coarse it to polygon. We'll remove donut holes and then we'll aggregate to create one giant clipping feature. From here, our FlatGeoBuf points are clipped again with our new clipping feature, and points are prepared for visualization. So they're buffered and we're setting a color. To actually have this color properly show up, we need to change the interpretation of the rasters. So that's what's happening in this bottom stream down here. We're coercing its interpretation. And then next, we'll have to combine our FlatGeoBuf points and our raster data. So we're using a vector on raster overlayer to actually combine the two data types, and we're generating a list of fire information, which is going to house things like its size, the status, what zone it's in. We'll notice the workflow split into two streams. So the top stream is going to create an image thumbnail of our raster, which will show up in each row of the table. And then the bottom portion here is actually creating our HTML report. So we're exploding that list we just made. We're removing any geometry because we really don't need it. We'll be extracting it from this top stream. We're doing some datetime functions, and we're accessing string format functions in the attribute manager. Once our rasters have been encoded in base64, we can actually remove the geometry again so that we're not processing rasters at each step of the translation. And we can join the thumbnails with our list information. From here, we can create the HTML table. And so we're going to use an XML templater. And the key in the XML templater is to actually disable this Ray XML header. So we want to set that to no. And that's so that we are only writing HTML here. We're not writing any XML bits or have any, we won't receive any extra XML artifacts in our output, sorry. Afterwards, we're going to format everything nicely in a HTML report generator and then push to HTML. So once I've reviewed everything and I'm happy with the workspace, we can go ahead and publish to FME Flow. In this case, I already have it published, so we can go ahead and jump into our instance. We'll select our workspace. We'll select the service, which is data streaming, and we're selecting data streaming so that HTML is actually streamed directly back in our browser, and we can go ahead and hit run. And so this is our output HTML. You can see we have a clipped thumbnail of each fire on the background DEM, a resource link to the fire, and some information. Assuming you needed to look for a specific fire, you could go ahead and search for it.
Awesome. So that kind of wraps up our second demo. So again, just taking a look at the output. And then the key demo takeaways. So here, FlatGeoBuf and COG readers support spatial filtering operations. So again, you can just read what you need. You can use Polygon Master, find points and no data areas of the raster. And the XML templater can be used to help format HTML elements like tables. So our last format before I hand it back off to Dean is FlatGeoBuf. So FlatGeoBuf is a vector format built on Google's FlatBuffers library, and we can think of a buffer like a file and everything kind of associated with that file. So taking a look at the format in FME, you'll notice that the search envelope is on the reader, but I'd actually like to highlight the verify file buffers parameter. And so the verify file buffers parameter will validate the file offsets and ensure everything is the correct size. And so by doing this, the library is able to recover from a limited amount of data incorrectness in the file, which is enabled by that integrity check. So once you kind of read with verify buffers enabled, you can disable it and you should see a little bit faster reader performance as it's going to skip those checks. On the writing side, we have this option to create a spatial index. And so index might help reduce the amount of data that would need to be transferred over a potentially slow network for those search envelope type of operations that we've been seeing on the readers. So if you're reading the entire file from the cloud or locally, having a spatial index isn't necessarily going to benefit you because it won't be used. I think maybe another reason you might not want to write a spatial index is if you're concerned about file size, it might add a little bit of overhead. So just disabling the spatial index would kind of cut back on some of the size of the file. And so this brings us to our last demo. So here we kind of use the Easy Translator app as some inspiration. And so here we made an app that will upload pretty much any vector data set to Amazon's S3 as a FlatGeoBuf file. And the motivation behind this is that we see a lot of users use FTP to receive data submissions from clients. And so we're kind of attempting to recreate that process, but using the cloud and FlatGeoBuf. So here I'm actually going to jump into my FME form and go through the workspace, and then we'll hop into Flow. So you can see we're using a generic reader to read our data with a merge wildcard applied. We're creating an attribute creator to store a coordinate system, and this way we'll actually give the user the ability to select the output coordinate system that the FlatGeoBuf will be written to. We're using a proj reprojector to actually use the user selected coordinate system here. And I have this online grids enabled. And so when publishing to FME Flow, this is kind of nice because by enabling these online grids, we don't have to have, any grid shift files kind of added in here. It will actually grab them directly from online. So it's kind of just reducing the dependencies of the workspace. We're using a feature writer to write to a temporary resource folder on our Flow instance, and then we're pushing to Amazon's S3. Depending on the success or failure, we'll be creating different attributes. So I think this will be the success port, and we're timestamping the date that the file was uploaded. We're using a second S3 connector to get a list, and this is really just confirming that the file we just uploaded is actually in the content. So we're grabbing a list of all the files in our kind of folder, and then we're formatting everything into an HTML report. So the service here will be FME data streaming again. And so you can see we've selected our workspace, we've selected the service. I have my data set already applied. I could go ahead and change the coordinate system that the FlatGeoBuf will be written in, but I'm going to leave as default, and I'll click run. Should just be a minute. Awesome. So the job was a success. We've uploaded this file, and we can actually see it exists in our list of folders, files. So just kind of to recap on that, so user parameters can help make workspaces more dynamic, and the proj reprojector kind of gives you a little bit more dynamic abilities too with the online grids enabled. And I think Dean's going to take over for COPC.
Awesome. Thanks, Kaylin. That was a great overview and running through a number of those very sort of diverse, different options there for cloud native formats. Let me just get my screen shared here. Make sure I'm sharing the right one. All right. And I also liked how you had an example of publishing it to Flow, because ultimately we do want to be able to leverage these in automating our workflows. So I'm going to dive into cloud optimized point cloud, COPC. And so we're looking at yet another data type. In this particular case, it's point clouds. So as you can see some examples here, point clouds are basically a 3D array of points that can actually have properties as well. And in this case, these have been colorized, so they have RGB properties, but they can have a number of other values on them as well. They typically are quite massive, so you can have gigabytes of data in point clouds. Can be generated from LiDAR, laser scanning, or by doing dense point matching, which is what I did on the top right image. And basically and it's all based on the last standard, so the LAS standard. And given the huge data volumes, yeah, it's an ideal candidate for cloud native. And a lot of these data sets there's a ton of data being published and continually updated. So essentially, it's similar to COG in the sense that we have the COP structure built on top of LAS. And the ultimate goal is to query the XY extents. So this particular data set was the result of the White Rock Pier storm event that happened a couple of years ago, South Surrey area. And you can see the stretch of the pier that was destroyed in the storm. And so I flew this with one of my drones and used Open Drone Map with dense point matching. There's a custom transformer for that on the hub if you're interested. And so that generated both a georeferenced GeoTIFF and a point cloud, a 3D model in terms of about 1.1 million points, which is kind of smallish for as far as point clouds go, but it's sufficient. It's nice for demos. So the first thing I did was convert from LAS to COPC. And then, so the key thing here is, it's interesting that the COPC writer still has a short name LAS, but it has this option of write it as COPC. So make sure you check that. We also, I chatted with developers the other day, and they were suggesting that in general compression, there's a bit of a trade-off. So we generally like to write compressed because that minimizes the footprint in terms of bandwidth. It does increase the process load on the client. So if you had a very, very light client, then you might have to play with what type of compression you're using. But in general, we do like to compress. And so this is only LAZ compression is supported for COPC. And again, make sure you set the coordinate reference system. That's very important. So similar to what you saw with Kalen, we have an S3 connector where we upload the data. In this case, we're overwriting, and we have a bucket over on S3 under Safe Experts. And so this is the demo I'm going to show you, where we're basically reading from that data set in order to do some analysis on the pier damage and kind of like assess, how much of the pier was destroyed and that sort of thing. So I'm actually doing some data conversion in terms of feature extraction. I convert from point cloud to raster, and then I use a raster to polygon coarser to generate areas. So without further ado, let's have a look at that. So let me pull up Data Inspector. I will go to COPC and pull up the LAS file. I don't have to set any parameters. All I'm doing here is showing you what the raw data set looks like. And this is local. That's why it came up so fast. So I'm not pulling this off S3. So you can kind of zoom in and see the different elevation values. This is height off geoid. That's why it looks so high, even though this is sea level. And so in terms of the actual workflow, so I'm going to run this. And so now we're tightening up our query to be just the area of the point cloud that we need to assess the pier. And so we'll see that that runs pretty quickly. So this is going to S3. I guess to do a proper comparison, I could have read it from S3, but anyway. So this is the part we're actually reading, and you can see that this particular part of the point cloud only is what we need right around the pier itself. Yeah, see. So it's pretty quick to access that. And then ultimately what we're doing here is we've extracted these polygons. We made polygons out of the pier for areas of elevation greater than, a meter or two above sea level. And so we can actually go and measure, how much of the pier was destroyed. In this particular case, if I look at my log, you can see that, a sec here. I have to clear my log. About 48 meters was destroyed. Yeah, so basically, you just wanted to, from the cloud optimization perspective, we have a very tight search envelope. Clip to search envelope is really key. And that's one of the reasons I'm, in terms of things that are coming, if I try to do this via feature reader, I think that's the basic problem for formats like COPC, is that there really is no option to clip by search. You can have a constraints and a spatial filter, but there's no clip option. And so that's something that we need to enhance if we're going to use this format effectively with feature reader. So that's something we'll work on. And then the other thing to mention, these array formats are quite easy to cast. So we convert from point cloud to raster with a numeric rasterizer. And I always tell people, if you're going to try to do conversion from point cloud or raster to vector, you always want to classify it first. So that's why I have these cell value replacers. So basically make a binary grid similar to what Kalen was doing before I pushed it through the polygon courser so I don't get millions of cells. All right, so that's pretty much all I wanted to show for COPC. Yeah, so it's optimized for the web. It's a pretty, this is pretty powerful because that way you could actually have a very large project file for, let's say you were scanning a work site or a project or even a city block. Every day, people could just extract the data they need. Again, read what you need. There were some fixes since the last webinar because when we were trying to make this, we ran into a few hiccups on kind of some issues that came up when we tried to read what we wrote. And so those have been fixed in 0.0. So I'm glad to report that. And yeah, the extends query support. There's been a few tweaks on that as well. So yeah. Now I'm going to talk briefly about ZARR. So probably a majority of you may not have heard of ZARR or worked with it too much. So it's a little bit more, I'll warn you up front, it's a bit more complex than the other formats we've talked about, like COG or COPC, because it's a multi-dimensional array. It could have 2, 3, 4, or 100 dimensions. So just think of it as a data cube, and so that's NetCDF is kind of the open standard that ZARR is based on. So they all kind of have an open standard that they're kind of on top of. And typically ZARR is used for things where you have multiple measurements over an area. So you might have temperature and salinity in the ocean. And it's also very commonly used for time series. So in this particular case, I have climate model output data, like RCP45. So that's, climate model, CMIP5. So this is just different climate model outputs. And so we have data for southern Manitoba, and we're just extracting the data around Winnipeg in this case. And so the time series from the climate models, you could have daily, weekly, monthly data over 100 years. So that could be a lot of data. So in this particular screenshot, we're just extracting half a dozen slices of data for Manitoba. And then this is the conversion from NetCDF to ZARR, as you can see, is, Don likes under 10 transformer workspaces, and this certainly qualifies. You don't have to actually do anything. So obviously there's some parameters on the ZARR writing, but you don't need any transformers. It will interpret the NetCDF and write it straight out as ZARR. And basically each time step is one band. So that's kind of cool. So I'll run through this demo. The purpose of this demo is just to do some analysis on the ZARR data, which is the climate data around Winnipeg. Just jump into that. In the interest of time, I know we're kind of getting a little tight for time, so I'm not going to rerun it. I'll just kind of step through a little bit what this is doing. Basically, we're reading ZARR from S3 and splitting it up by time step, and we're looking for hotspots. So in this particular tester, we're looking for monthly max greater than a certain level. We're also doing raster statistics, and this is quite powerful. In the raster mosaicer, we can basically group by month and say, okay, for all the months, what is the hottest temperature? What's the hottest August going to look like? And then what we're doing, we're using a raster cell value replacer here to kind of filter. Again, when you're doing raster to vector conversion, I always like to classify. So we're kind of filtering this into different temperature bands and then converting those to polygons and styling them by color. And so when I run that, I can run it in the background if you want, just to prove that it works. I'll do that after I show you the output, when I get through the rest of the talk. But here, I'll just show you what that looks like. Yeah, so here's one of the temperature steps for August July, and you can see that this has got a grid around Winnipeg, and it's there's a little bit of. I find that the data inspector takes a little while to render these things, so that'll come back in a sec. And then this is the max temp by month, and then we have some hotspots. So yeah, this is the vectorization of that. So you can see I've kind of got the kind of these temperature bands. These are the hotspots, and I can see that in 2030, the climate model is saying that some of the hottest temperatures are going to be in the year 2030, July, because this is a monthly data set. So here are some of the point values for those temperatures, and the temperature here, 21.9. And that's the average monthly temperature day and night. So the maximums could be well into the upper 30s for that time step. So let's see if, I'll just turn this off and see if I can. Yeah, so I can inspect some of these values. You can see a hot temperature of 21.92, cooler 21.7, and then these are the kind of the raster, the vectorized polygons. So so this band here, the label has the temperature value. So label says 22, and then this band, the label is 21.5. Yeah. All right, so just, I mean, one of the goals with all this, I'll just flip back to the deck. Just a little bit of context for all this is that we've been doing a fair bit of work with, I just wanted to mention this. This is one area where I noticed there's a bit of an issue in the log where it basically says, start reading from feature 100. We'll read a maximum of 132, but it's actually reading everything up to max feature and ignoring the first 100. So I think we could do a slightly better job. I'm using a scripted parameter in Python to calculate which band to start reading from and which band to stop reading. But for that to be fully optimized, I think we could enhance the reader to ignore everything until the start feature, because right now it's reading everything up to the max. So there's a little more work we can do there to fix that up. So I just wanted to give a quick nod to the OGC and the work they're doing. So that they've got a number of pilots that we've been participating on in the area of disaster response and climate change impact. This is sponsored by Natural Resources Canada, NOAA, Homeland Security, and a number of other agencies. So this really, we find this benefits us because we get to work with real use cases with these formats, and it kind of kick the tires on our performance, and it also helps us to interact with the geospatial community and to contribute to some important areas of development. So this is just a snapshot of what some of these data cubes look like. And one of the questions we wanted to ask was, in the next 40 years, which areas are both 25% drier and significantly hotter? And so we did some raster math to do that, and we found some areas south of Winnipeg that kind of fit the bill. So that would be kind of a high risk area for drought, let's say, for agriculture impact. So just to summarize ZARR, and then we will I'll step through a couple of slides on GeoParquet, and then we'll wrap up. ZARR is a multidimensional raster array, often used for things like time series as well as multiple measurements. Again, we want to be able to support read just what you need. And each time step is a separate band. Right now, we do support the read what you need on terms of XY extents, but there's sort of partial support for band ranges, and so we're still going to be working on that. And just a few quick notes about GeoParquet. So Parquet has been around for a while, and there's a lot of tools out there for it. And so that's one of the probably motivations behind GeoParquet. So it's highly optimized for accessing huge data stores where you only select the columns that you need. And so again, there's no one size fits all, but if this fits your data set, there's a lot of tools out there that support it. And of course, GeoParquet adds support for a range of geometries, but the main limiting factor is there's no overt like spatial index. So you have to use things like partitioning or DuckDB to subset the data. So how do we, so GeoParquet, in terms of how do we support reading huge vector data sets? And so the demo here, and I'll make this workspace available. It's a fairly simple one where we basically read a GeoParquet data set stored in different locations. And then we do a filter on that. So we take, basically 1 million records, filter it down to 100,000, and then compute statistics on that. And so I ran this workflow in a number of different scenarios, including with partitioning. So when you actually write out data with partitioning, what it will do is it'll break it up into separate data sets. And that way you have a different, basically a different GET request for each of those partition data sets. So yeah, you basically have, like in this particular case, you can see that the GeoParquet, there's a nested file structure beneath it for the different types of different classifications of the data. So here's just a quick comparison. Reading data locally obviously is quite fast. Cloud to cloud is also fairly quick. So the slowest is probably cloud to local. And you can see if you have this same data set of, water bodies or hydrography access stored in OpenStreetMap, it takes over a minute. GeoPackage, it takes even longer because it has to download the whole thing before it can start reading it. So even though the GeoPackage is spatially indexed, because it's larger even than the OSM, the biggest bottleneck is the download. Converting that to GeoParquet without doing anything particularly special, it's down to half a minute. And if you have partition data, it's 15 seconds. So you can see the kind of testing you can do to compare performance in different architecture or environments. So the quick lessons learned here are, this is a column-oriented format. We found it on overall is about 2 to 3 times faster than the alternatives. But cloud native for vector is just not as easy as it is for raster or point cloud. That's not really anybody's fault. It's just that raster and point cloud are very predictable arrays, 2D or 3D arrays. And so subsetting them, we can partition those ahead of time in a way that meets most use cases. And that's not as easy to do with vector. With vector data, and even with, you could argue with ZARR, you kind of have to understand a bit of the use case for the data in order to figure out how you want to subset it. And so partitioning is one approach. I have a link here to DuckDB, and Chris has an article that he published on the Cloud Native Foundation about using DuckDB with GeoParquet to improve performance. So just to wrap up, this is a nod to cloud databases. So there's a lot of ways of publishing database data on the cloud. We did not, that was kind of out of scope. We didn't cover that today. But we do have a past webinar on that. There's a link on the resources page. So if you are interested in publishing data to, let's say, Amazon Redshift or one of these others, Snowflake, do check out that webinar. It's really good. So the integration strategies that we recommend is just start publishing something and play with it. So that's the best way to learn, is get your feet wet. With FME, we make that easier. There's some basic principles here about keeping your processing close to the data. So if you have FME hosted next to a S3 data store, it's going to perform a lot better than if you have it on-prem. Always think about what your traffic footprint is, and that's why we talked about compression. Just keep that transaction size small. Leverage data side filtering when you can. So let the server or let the service or the database kind of do the work if you can, and keep your data enriched and up to date. And ultimately do lots of testing. So basically with large data sets to structure the data, you're going to have to do more work on the upload side, but that will make the access faster. FME helps you because you can do those updates, you can automate that. And we also stay on top of all the third-party library fixes. There's a little bit less data available for some of the newer cloud native formats like COPC, ZARR, and STAC and COG have a ton of data out there available. And I already mentioned DuckDB. So yeah, just to wrap up, a couple of lessons learned, and then we'll open it up for questions. Cloud native is all about making it easy to publish your data without a server, sort of a serverless architecture. You just publish your data to an HTTP endpoint, and you can just read what you need. And makes it a lot easier to build up that spatial data infrastructure. There's no one size that fits all. So for example, STAC is a great metadata catalog. It's a little bit of a learning curve to figure out how that works because you can have collections within catalogs and vice versa. Also, we find that the implementations we looked at, everybody seems to do things a bit differently. There's also different security requirements where you might be able to see the stack, but not the COG, for example. COG and STAC probably have the most data. COG and COPC are probably the most intuitive because we said 2 and 3D arrays are probably overall easier to manage. Vector cloud native is still evolving. FlatGeoBuf seems to be a bit easier to configure because it's already spatially indexed, but GeoParquet has a bit more tooling. And ZARR is powerful, but fairly complex, and it's a kind of a niche format. So yeah, just to sum up, cloud native is all about making it easier to publish your data, read just what you need, which just demonstrates SAFE's commitment to supporting emerging standards as well as open standards. And open standards is really foundational to all of this, so that allows you're not locked into a specific vendor. FME makes it easy to support hybrid environments so you can move the data to where it needs to be. In general, keep your processing close to the data. Always think about your traffic footprint, and there's no one size fits all. So you need to look at your specific requirements and do lots of testing. So that's probably all I'm going to cover today. There's lots of resources here. There's a brand new that Kaylin just published yesterday, 1 day ago. That's accurate. And so we're going to have a bunch of the starting point landing page for cloud native, and then we'll attach tutorials and things to that over time. So I guess there's a lot of data sources there, obviously more for STAC and COG than ZARR and some of the others. And next steps is more blogs and tutorials coming, lots of events with folks like the Cloud Native Geospatial and with OGC. There's an OGC meeting up in Montreal next month, and new functionality. So we want to hear from you. What aspects of Cloud Native are we doing well at? What new functionality are you looking for? Do you want a specific DuckDB reader-writer or better ZARR band range support, more media types for STAC? So I'll open it up for Q&A.
Yeah, and in the meantime, I'll just note as well, I know we're at the hour here, so if you have to drop off, thank you so much for joining us here today. And I did drop the community badge code in the chat as well, so as a thank you for joining us if you're a part of the community.
Yeah, so I see a question that Reed just asked. Just wondering if cloud native formats would work with a CDN environment.
What type of environment?
I think it content delivery, a CDN. Sorry, my mic's a little hazy here.
Yeah, for sure. If you are distributing data to a wider audience, cloud native really makes a lot of sense. like I think I mentioned before, if you're hosting data in the cloud, you, as the author, the hoster of that, you typically have to pay for the traffic, both the hosting, the size of the data, but also the access of the data. And so by using cloud native, if you had some large GeoTIFFs that you converted to COG, the amount of downloads could drop dramatically in terms of the footprint, and that could save on your costs, and it would also ease access for your customers or for your users. Yeah, so I think that's a good example.
Okay, and another one I see asking about a cloud optimized format for 3D textured meshes, and if FME is able to support that format.
Well, when you get into 3D data, usually people, I would say most of the use cases I've seen have been more in viewers. And so we support, as from Esri, from the SRI I3S, as well as the Cesium 3D tile standards. And those are very efficient. They're they're web optimized, I should say, for viewing and interacting with 3D data. Now that's for viewing data. That's not specifically for downloading. I am not aware of a 3D format that has been optimized for cloud access. So if there is one out there that we aren't tracking, let us know. You might be able to have a 3D geometry object in a column in a Parquet table. So there may be ways of and I know that FlatGeoBuf does handle multiple geometries types, but Kaylin, do you remember offhand if it handles 3D data or is it limited to 2D?
I recall one of them I think had surface support, but I can't recall which one it is. I'll take a look right now.
So yeah, FlatGeoBuf may be able to handle, let's say, a 2.5D use case if you want to have surfaces. So that would be one option. I did notice somebody talking about subsetting the data and what strategies to have about tiling and subsetting. And it's hard to kind of come up with sort of a generic response. A lot of that depends on what type of data you're dealing with, which of these formats you're going to work with, and what's the use case. And so, like Kaylin, I noticed that you decided was it a tile size of 512? Was that pixels or bytes?
That was the size of the tiles on the COG output.
Yeah. So again, it'll depend on, well, what's the size of imagery, what pyramid levels are you going to support? And so some of that you will indirectly configure when you define how many pyramids levels you're generating. And then FME will auto-generate the tiles based on that. And some of that you can configure like Kaylin did. And ultimately, I strongly recommend just trying a few, configure a few different options and then test and see how it works for your data. But we're happy to follow up offline if you have a specific question on that.
Awesome. Yeah, Natalie or anyone else, is there any other questions that we see we haven't gotten to yet that we want to address here?
Or anything in the chat that came up?
I see one that just came in about protobuf, the protobuf format, and whether FME supports that format given our support for FlatGeoBuf.
I think we have an OpenStreetMap PBF writer.
Yeah, we have a reader writer for protobuf, but I guess it's the OSM profile. I don't know if there's a generic protobuf. And Kaylin, correct me if I'm wrong, but I don't believe the protobufs, while they are used for things like OSM, I don't think it's inherently cloud native. Like it may be indexed, but if you had a large file, you would probably have to download the whole thing before you could start reading it, right? As far as I know.
Yeah, I think you're right. But we could double check that again.
Yeah, I'm pretty sure we do support it, or at least some profiles of protobuf. I think protobuf is a sort of a pattern or a sort of like a storage medium, but can be there's a profile for that for OpenStreetMap, and there's probably used in other formats as well. Good questions. Yeah, thanks for, looks like there's been a fair bit of chatter. Anything we don't have time to address in the webinar, we'll definitely follow up afterwards. And I do appreciate you spending the time with us today.
Yeah, thank you.
Thanks, everyone, and hope you all have a great rest of your day. If you have a moment to fill out our webinar survey, we appreciate any feedback. And yeah, with that, we will bid our adieu and hope you all have a great rest of your day. Bye for now.
Yeah, bye, everybody. And thanks, Kaylin and Natalie and Elizabeth as well.
Yeah, likewise.
And stay tuned for whatever our next webinars.